Hi, good evening, everyone. Welcome back to yet another PyData Pune event. As usual, before moving to today's agenda, I would like to take this opportunity to give a brief introduction about PyData and its mission. PyData is a non-profit initiative of NumFOCUS through which they provide a platform to community for sharing and interacting on the grounds of data and associated genres. The Global PyData Network promotes discussion of best practices, new approaches, and emerging technologies for data management, processing, analytics, and visualization. Tonight, we are here with a great talk for you titled as Efficient Modern NLP, an overview by Hugh. Hugh is a science enthusiast uh, who is always hungry for new knowledge. He pursued a mathematics major at one of the top public universities in Indonesia. Currently, he is into natural language processing. Uh, he has experience in both the engineering and research side of NLP for production. So without further ado, over to you, Hugh.
Hello. Um, Hello everyone. My name is Hieu, and I'm very happy to be invited to this talk. Um, a little bit clarification. So I studied in the United States for 5 years, and then I returned back to my country in Vietnam. And right now I'm the machine learning engineer in Vietnam. And I have some experiences working with natural language processing models, and have been deploying them to production, as well as I have to uh, read papers and learn about different algorithms of NLP, so that it can balance between efficiency and accuracy. And so today, that is the topic of my talk. So the topic of my talk will be about how can we deploy natural language processing models to production that can balance between both accuracy and efficiency, such that the models is not too big and is fast enough to be production ready. And so this talk will talk about different algorithms and their papers and how it works, and also because it's geared towards engineers, I will provide links of each models. And I carefully chose these types of papers because they have been implemented into Hugging Face, a very popular NLP framework, and also they also have their own official implementation. And so engineers who want to start using them right away can find it very easy. And so I will start with my presentation. This is the talk will be divided into 5 sessions. So the first is I will talk about the overview of transformers and BERT, which are the two state-of-the-art architectures since 2018 and 2017, as I remember, as transformers was introduced. And the second section will be about the efficient transformers. So how researchers have made the transformers more efficient. The third section will be about efficient BERT. So what researchers and engineers have made the BERT model more efficient, both in terms of time and memory. And the fourth session, I will have a small demo. So I made a small demo to test whether these models in real data can be efficient or not. And the fifth session will be question answering. So I will see your questions and I'll try to answer or to provide resources as best as I can. So the first session is overview of transformers and BERT. So what are the applications of transformers and BERT, specifically and NLP in general? So for those of you already work on NLP, you probably know about these tasks. But for developers or engineers in general who are new to machine learning or NLP and wish to learn more about what can I do from these models and what can I do from this talk, then I'll briefly introduce the tasks that NLP tries to address. So the first task is machine learning translation. Transformer is originally developed for machine translation. So for example, Google Translate translating from English to Korean or English to Chinese or vice versa, or any pair of languages or machine translation. And that's one task of NLP. So another task is sentiment analysis. So for example, you want to, you are the owner of an e-commerce website and you want to know whether the review comments are positive, neutral, or negative. Or for example, you want to monitor the Twitter data, whether how they talk about your company, or you want to play with the stock market based on Twitter data, for example. Question answering. So for example, if you type in some keyword on Google, if you try to search something, you will probably see in some cases you see that Google tries to have some questions and then the answers below. So question answering is when given a body of text, you ask a question and that question has some answers inside the text, and then the output will be the answer based on the body of text and then your question. Text summarization. So so also if you Google a lot, you will see that Google sometimes tries to summarize the wiki pages. So the summarization of, so I don't know the insights of Google engine. So could be the summarization that wiki provides themselves, or could be that the neural architecture of Google that tries to summarize the wiki pages. Text classification. So one of the newest application of Facebook hate detection. So for example, you see a lot of toxic comments or toxic posts on Facebook. So Facebook tries to utilize neural architectures, deep learning to detect the posts or detect the comments so that they can be in further review. Or semantic search. So semantic search is when you try to search something with a large body of text. So for example, Google has actually announced that they apply BERT model inside their core search engine. And this is really big for all websites that try to make their way to the top of the Google search. And it's not just about Google search, but also enterprises using semantic search for deep search over the raw text data. So So, for example, a large corporation have a huge data lake of unstructured text data, and they want to utilize the knowledge of this text. So, using just a simple solution like Elasticsearch is only about like keyword matching. So, having a deep learning solutions to have a deeper understanding of those body of text would be a much better solution. And transformers architecture is not just about text, not just about NLP, even though it starts with an NLP application, which is machine translation. Transformers architecture has actually been researched into different other domains, such as computer vision. So a paper from Google, as I remembered, they Google or Facebook. So they use transformers to apply to computer vision tasks. And what they found is they also achieved a very competitive results compared to the traditional convolutional neural networks. And so the hope of those researchers is that transformers can replace CNN in some cases, or even all cases, when they utilize it to computer vision. Another area that people try to apply transformers is structured data, so tabular data. So if developers have been trying to, or data scientists have been trying to use traditional machine learning methods like boosting or tree methods, now they can have another toolbox in the skill set to use transformers to apply to tabular data, and there have been papers on those applications as well. So the ambitious goal of just transformers architecture is to replace both recurrent neural networks and convolutional neural networks for an unified model. And we will see in the future if that can happen. So what are the problems with transformers and BERT? So the biggest problem is they are very large models. So they have slow pre-training and training time, and also they have a large memory consumption. And that is when you train models. So when you deploy it to production, they have a very slow inference time. So so it is very good for researchers and also companies with huge budgets for GPUs to do training and inference on those models. But for a lot of other companies, they don't have such luxury. So so improvements are needed for widespread real-world applications. So before we go into how to make transformers and BERT more efficient, when we look at researchers' work, I will go through the overview of what transformers are and what BERT is. So in every slide, I have put the reference in the below text, so you can see where I get sources from. So the transformer is from the paper "Attention is All You Need" from 2017. They are invented by Google researchers, and the goal of the transformer is to replace the already very popular architecture of recurrent neural networks, and by doing a completely different architectures. And so a little bit of history. So recurrent neural networks have been using attention to improve the long range the long range dependency. So recurrent neural networks without attention suffers from losing information when tokens are far away. So recurrent neural networks using attention remedies some of those drawbacks. But researchers see that what if we use only attention? So that's the reason why the name of the paper is attention is all you need. So the whole architecture is attention. So no recurrent neural networks inside the model. And the task is the machine translation, and it's just a standard machine translation task. And the error function is a standard cross entropy error on top of a softmax classifier. And in here you can see the architecture of the transformer model. So the inputs is the source text. It is embedded and encoded, and then it goes through the multi-head attention, which I will briefly explain next slide. And then it will go through has a residual connection here, and then it will go through the feed-forward fully connected neural networks here, and then another residual connections. And then for the decoder is the same thing, except the masked multi-head attention. And it goes through the whole process, and then it goes with the standard softmax and then output probabilities. And so for the attention, which is the core of the transformers model, you can the most important thing is the softmax, this equation. So the attention of query key values. So when speaking of transformers and BERT applying to NLP, especially for BERT, query key values are the same input embeddings. So for the first layer, so the equation here is the softmax of query times the transpose of key, and you take that and you times values. And this is where the inefficiency of transformers start to show, and this is where the researchers want to reduce the complexities of this function. For BERT, so BERT stands for bidirectional encoder representation from transformers, and BERT is the core of BERT is the transformers encoder, and the way they use BERT is to pre-training BERT into a corpus or a body of text, and then you fine-tune it for a specific task. And the goal is to have a truly bidirectional information without leakage in the deep model. For more information about BERT, you can read the original paper, or you can read some of the summaries of the paper. So I have some summaries here. So transformer encoder is, as I mentioned, it doesn't have the transformer decoder. It uses self-attention, so it doesn't have any locality bias. So which means that one token can attend to all other tokens without losing information as recurrent neural networks. So equal, they have, all tokens have equal opportunity in quotation mark. And they especially they can utilize the efficiency of GPU, because for recurrent neural networks, they can they don't have the because of the architecture, then they cannot utilize the parallelism of GPU, whereas for transformers model they can. And they train on the Wikipedia and Broke corpus, and they have two model size: BERT base and BERT large. And it takes a very, very long time to pre-train the BERT model. So for GPU time, you can imagine like it takes even weeks or months to train on GPU. Of course, depending on the GPUs, but for normal GPUs, it takes a very long time. So for example, a sentence like "My dog is cute. He likes playing." Then it will tokenize the sentence, and then it will embed it with a lot of information about this sentence. For example, which sentence it belongs to, or for example, which position it belongs to, and then some of the special tokens like CRS is a special token for classification tasks. Between each sentence, it have a separate the SEP token. So all of this, if you use a framework like Hugging Face, then they already do all this for you. So you only need to care about the input. So this is the input that goes into the BERT model, and then they will start the pre-training and fine-tuning. And then for fine-tuning, you simply learn a classifier built on top layer for each task that you want to fine-tune. So that is the overview of transformers and BERT. And now for the second section, I will talk about the what researchers have found to make the transformer more efficient. So as I said briefly before, so what is the original transformer architecture problems? So first of all is attention computation. So computing attention on sequence of length L is O of L squared, both in time and memory. So imagine if you have a very large sequence, right? And the second is they have a large number of layers. So for example, a model with n layers consumes n times larger memory than a single layer model, as activations in each layer needs to be stored for backpropagation. And the third thing is the depth of the feed-forward layers. So the depth of the intermediate feed-forward layers is often much larger than the depth of attention activations. So how can we address this for three issues? So introduce reformer. Reformer is accepted at ICLR 2020. So all of the papers I introduced here were accepted at as a workshop or as a full paper or in the main conference of all the top AI conference. So Reformer was accepted at ICLR 2020, and I include in here the official code and also the Hugging Face implementation and sometimes pre-trained models. And the summary of Reformer is it reduces time and memory complexity of transformers. And you can also see the paper link below the slide. So the reformer model addresses the three main sources of memory consumption for the transformer. It can handle a context window of up to 1 million words, all in a single accelerator and using only 16 GB of memory. And the final reformer model performed similarly compared to a transformer model, but show higher storage efficiency and faster speed long sequences. So that's what we care about when we make it more efficient, right? So it can be more efficient in terms of time and memory complexity, but if it performs with much worse accuracy, then it is not a good alternative of transformer. So it needs to be efficient in some types of time or space complexity, but it also needs to be accurate or competitively accurate with the original transformers. And so Reformer achieves that by combining two techniques to solve the problems of attention and memory allocation. So first technique is locality sensitive hashing, LSH, to reduce the complexity of tending over long sequences. And the second technique is reversible residual layers to more efficiently use the memory available. So so we go back to the equation I mentioned before. So the issue here is the query times key transpose, which is the complexity of L squared, right? So how can we reduce the complexity of this equation? So the researcher noticed that we only care about the softmax of query and key transpose. So if we can reduce the complexity of the softmax equation, then we can make it much faster. So because softmax is dominated by the largest elements, for each query, we only need to focus on keys that are closest to Q. So for example, if K is of length 64,000, so for each Q, we could only consider a small subset of, for example, 32 or 64 closest keys. So if we can do that, then we can significantly reduce the computational cost of the softmax equation. But how can we find the nearest neighbors among the keys, right? So how can we do that? So they use this local LSH, and the intuition here is that so imagine you have a sphere projected points, and imagine, so for example, if you have 2 points that are far from each other and 2 points that are near each other. So for 2 points that are far from each other, when you do random rotation many times, you will see that the probability of them belonging to different parts is higher, right? And so the hash value will be different, will be more different than, for example, if you have 2 points that are nearer. So when you do random rotation, you will see that their hash value will be more similar. So using this technique, they sort by the LSH bracket, and they chunk them to parallels the training, and they only attend to the same bucket in the own chunk and previous chunk. So so for example, before, for transformers, each token here have to attend to all other tokens, but in here, after you sort by the hash values, you only attend to their own chunk of similarity. And the second idea of reformer is the reversible residual layer. So it uses the technique of a previous paper of RefNet. So RefNet improves ResNet by thinking, how can we do backpropagation without storing all the activations inside the memory? So I won't go into details here, but you can look it up in the paper, and it is a very brilliant architecture, and it's not just only for reformer, but also for computer vision tasks. So using the RefNet, they won't need to store all the activations of transformers inside memory. They only need to store, as I remember, the final activation values, and then they can, when they work it back, they can recalculate the activation of each previous layer. So that is the reformer paper overview of efficient transformers. Now I will talk about the efficient BERT. So the first paper I'll talk about is ELECTRA. So ELECTRA is accepted at ICLR 2020. And I also provide the official code here from Google Research, and also the Hugging Face implementation. And the summary of ELECTRA is it improves pre-training tasks and methods of BERT to improve the pre-training task. So the idea of ELECTRA is to introduce a pre-training task. So in BERT, there are two pre-training tasks: the mask word, the mask word modeling, and also the next sentence prediction. And ELECTRA introduces a pre-training task that get the idea from GANs. So it has a generator, so typically a small mask language model, right? And then a sentence here will be mask, and the generator will generate the prediction of what it guesses from the mask. And then the discriminator will have to predict whether which one is the replaced and which one is the original. And although similar to the training objective of GAN, there are several key differences. So first is, if the generator happens to generate the correct token, then the token is considered real instead of fake. So they found it moderately improved results on downstream tasks. And the generator is trained with maximum likelihood rather than being trained with adversarially to fool the discriminator. And lastly, they supply the generator with a noise vector as input, so typical with GAN. So they don't backpropagate the discriminator loss to the generator. And so they throw out the generator and fine-tune the discriminator on downstream tasks. And with that, ELECTRA matches the performance of Roberta and XLNet. So those are also variants of BERT, which also achieves very high accuracy on the GLUE natural language understanding benchmark when using less than 1/4 of the compute, and achieves state-of-the-art results on SQUAD question answering benchmark. So it matches the performance of really high score models while using only like 1/4 of the computing. And with ELECTRA Small, you can even train the full pre-train the full ELECTRA model with only a few days using a single GPU, and with better accuracy than GPT. So it really makes the individual developer or programmer life much easier when they don't have access to a large GPU. And this is the graph that we can see from ELECTRA. So ELECTRA Small is already better than GPT for the GLUE score. ELECTRA Base is already better than BERT Large, right? Even though ELECTRA Base architecture is the same as BERT Base. And ELECTRA Large is already very competitively better than Roberta. So that is ELECTRA. So I'll move on to the second model, which is DistillBERT. So DistillBERT is accepted at the 5th workshop in New Rips 2019. And I also provide the official Hugging Face code. So the DistillBERT is developed from the Hugging Face team. So I think this is also like the official code too. So the summary of DistillBERT is to distill knowledge from teacher Bert to spoil a student model. Distillation is not a novel method that this paper introduced. It was introduced earlier by earlier researchers. So this paper uses that technique to apply to BERT. And so in the teacher-student training, they train the student network to mimic the full output distribution of the teacher network. And rather than training with the cross entropy over the hard targets, they transfer the knowledge from the teacher to the student with a cross entropy over the soft target. So they don't use the hard target of 1 and 0 of the softmax. Rather they use the soft target. So they take all the probabilities that the teacher produces, into the student. And so the training loss is the standard cross entropy. And to further expose the mass of the distribution over the classes, they use the softmax temperature. So if you're familiar with the softmax, usually the T here equals 1. So it was, but when they introduce the T parameter, it makes the label more smoother. So, and that is when doing the training time. So during the inference time, they make the T equals 1 again. The third method is the MobileBERT. So MobileBERT is accepted at ACL 2020. So ACL is one of the top NLP conference. And I also provide official code. So apparently it is also from Google Research, and also provide the Hugging Face code so that you can easily use it. And the summary here is it is the same the same inspiration from the teacher-student method. So I won't go into details here. And they use it to improve the memory. And the fourth paper is also have the inspiration from the custom teacher-student methods. So and this paper is accepted at New Rips 2020, which is this December. So they haven't had the conference presentation yet, so it will be upcoming December. And this paper is so from the official code. They are developed by Microsoft, and the Hugging Face code is also available. The fifth paper is DBERT. So DBERT is accepted at ACL 2020, and I also provide the official code and the Hugging Face code. So the summary here is to improve inference time by exiting early when sample passes through each layer. So for this paper, they don't significantly change the architecture of BERT, or they aim to improve the pre-training time like previous layers do. Rather, they focus on improving inference time. So after you do pre-training and fine-tuning, when it comes to inference on production, they can significantly improve the inference time. And the idea here is actually very simple. So this is the architecture of the model, and I'll explain further in next slide. So here, it inserts extra classification layers called off-ramps between each transformer layer of BERT. All transformer layers and off-ramps are jointly fine-tuned on given downstream datasets. And so at inference time, after a sample goes through a transformer layer, it is passed to the following off-ramp. If the off-ramp is confident of the prediction, then the result is returned. Otherwise, the sample is sent to the next transformer layer. So going back to the previous slide, so during inference time, every sample goes through a layer, right? And then at each layer, it evaluates whether this is the accuracy and the confidence level is high enough. If it is high enough, then it exits the layer, so it won't go through all other layers, and it exits it, and then that's it. So and you get the inference. Otherwise, if it's not high enough, then it continues to the next layer. And the reason why it is very fast is because each layer here has a really large number of parameters. And so by exiting early, it doesn't have to go through all of the layers. So for example, BERT base is 12 layers, right? Or BERT large is 24 layers. So by exiting early, it won't have to go through all of the layers if the threshold is passed. So dBERT is capable of accelerating model inference by up to 40% with minimal model quality degradation on downstream tasks. And dBERT is inspired from computer vision. So in deep convolutional neural networks, higher layers typically produce more detailed and finer grained features. So so people who know about computer vision can have more intuition from this model. So the authors have a hypothesis that for BERT, features provided by the intermediate transformer layers may suffice to classify some input samples. So the hypothesis here, as I just mentioned, is that you don't need to go through all the transformer layers to get the efficient accuracy as you want. And the sixth paper that I want to discuss is BERT loses patience. So it also have the same intuition. So I won't go into details here. So it's accepted at NeurIPS 2020, and you can access the official code, Hugging Face code here. So that's all for the paper theory. So I have some demo that I can show to you, as I said before. So this demo is question answering task from Wikipedia article. So I will get the any article from Wikipedia as I want, and then it will provide me with a paragraph of the Wikipedia article, or in here I think it's a summarization that Wikipedia provides for me, and then I will try to ask some question and you'll get the answer. And I will try it with different model types so that you can see the inference time and also like the loading time of each of those. So so here I use COVID as a search term. And so the question I use is, what are the symptoms of COVID? And the model here I use is ELECTRA small, so which is the small model using the ELECTRA algorithm to train the model. So you can see how it performs in terms of accuracy and in terms of time. So in here you can see that the answer is very accurate. So the symptoms of COVID in the paragraph above, here is a fever, cough, fatigue, breathing difficulties, right, and loss of smell taste. And the time is very fast, so it's around 2.5 seconds. So now I change it to BERT-based. So those models are already fine-tuned on a SQuAD 2 question answering task. So which is why I think it makes it very accurate. And so let's see how long this model takes. So you can see here the answer is also very accurate, right? Very similar to the previous one, and the time is 6.5 seconds. So you can see that the BERT-based is much larger and slower than ELECTRA. And also note that in this demo I only use CPU for inference. So this is not GPU inference, this is CPU inference. And so let's try the last one. So the last one is BERT large. So so BERT base is 12 layers, and BERT large is 24 layers, as I remember. So BERT large would be much more slower than ELECTRA small or BERT base. So let's see how it performs. So for the answer is also very accurate, right? Of course, like I think like the larger the models, it should be more accurate than like the smaller models. But and the time is 8.1 seconds, so much lower than much lower than BERT-based and ELECTRA small. So this is so you can test it at home too. So uses the Hugging Face code or using some implementations, and then try to benchmark it with your data to see how it performs on your data in terms of accuracy and in terms of efficiency. So that is all for my presentation, and now is the question answering time. Should I stop the sharing screen?
Hi. No, that's fine. So we have one question, and
Sure.
it is related to basic NLP thing. So the question is it always a good practice to combine NLP with deep learning for better performance?
Yes, so this is a
Kindly
great
share
question.
your.
Sure, yeah. So so when people think about, deep learning, wow, like this is really cool. Like I have to use neural networks in everything, right? And if you work on production, this is actually not the case, because so in terms of both, right? In terms of accuracy and in terms of efficiency. In terms of accuracy is easy to understand, right? So how does your model perform in terms of your data and also unseen data, right? So that is one metric, but it's not the only metric. And it's not always that deep learning methods, like for example transformers or BERT or recurrent neural networks works well or works best with text. So sometimes even like SVM or some Bayesian methods perform competitively, or even better in some cases than neural networks methods. So and that's the accuracy metrics. And the second metric is the efficiency, right? So that's the whole point of this presentation, right? So do you have the time to pre-train the model? Do you have the GPU resources to pre-train the model? Do you have the GPU resource to do inference on the model? So and what is the time constraint that the users of the website needs to see the results, right? So if the model is very large, and when you put it into inference, and the users see like a huge times like a time lag of your website, then you shouldn't be using that model, right? Or you should improve from that model, or you should use another model, or maybe like you purchase better GPU for inference. So yeah, so the answer here is take deep learning methods into account and try it if you have enough resources in terms of time and GPU, and also consideration for your users. But it is not automatically like the best way. It has to be, you have to try. You have to try with both the traditional machine learning methods and the deep learning methods. I saw a question here. So does Google uses BERT or deep learning model for auto-filling when typing any search query? So I have, I don't know what Google actually uses for search other than their public announcement. So I know that from public announcement, they said that they incorporate BERT to their search engine, but I don't know the insights. Yeah, feel free to ask me any other questions. Are there any other questions or?
Hugh, let's wait for another 10 to 15 seconds. So if any questions, if you
Sure.
see any question, then we can take it. Otherwise, let's move on to concluding.
Sure. How about we can we chat a little bit, like about for example, about well, how about your questions? Do you have any questions for me, or can you talk more about the PyData in Pune?
Sorry, can you repeat what you were
Yes.
saying?
So do you have any questions for me, or for example, or can you talk a little bit about like PyData in your community, like a little bit of activities in there?
Yeah, so one thing that I would like to ask is that we'll get the link of PPT, right?
I'm sorry.
Okay. So let's conclude this session. I think we do not have any more questions.
Sure.
So can we conclude? Okay.
Yes.
Yeah. Yeah. So thank you, everyone. We are very grateful to you, Hugh, for sharing your time with us. Thanks a lot to everyone. This talk will remain on YouTube. So definitely we would like to read it and we would like to go through it once again. And hopefully we'll connect with you soon. Thank you.
Yeah. Thank you, everyone. Thank you for inviting me to the talk, and thank you, everyone, for your great questions. Okay. I saw a question, right? How graph modeling plays a role in NLP. So I have not used graph modeling in NLP myself, but I have read papers. I've seen other people's work on using graph neural networks on NLP. So if you're interested, you can look up graph neural networks, and also you can look up uh, I would say knowledge graph, kind of like the traditional way of doing NLP. But yeah, for modern methods, you should look at graph neural networks. I've not personally used it myself, but I've seen works of people with it.
Okay, so I think this is it, Hugh. Thank you once again. And thank you everyone for joining us on YouTube. Thank you. Bye.
Yeah, thank you very much. Goodbye, everyone.